Hi everyone. Today I'm going to talk about the QCD modeling of uncertainties on particle spectra from dark matter annihilation. So this talk is based on work in collaboration with Simeone, Sasha, Roberto, and Peter, and it has been published in 2019. So I think there have been a lot of talks about dark matter, and so basically I'm not going to talk about the problems of dark matter or its origin, but I'm going mainly to be interested in the particle physics modeling of dark matter indirect detection. In principle, in many beyond the standard models, dark matter is expected to be annihilated to a number of finite states, which are quite model dependent. So either we can have WW or QQ bar or CT bar or any other finite state. And these finite states will undergo a set of very complicated processes before we can get stable particles such as photons, positrons, antiprotons, and neutrinos. And therefore, it's impossible to predict the spectra from first principles, and only we can use phenomenological models. The thing we can use is that these phenomenological models are basically depends on many parameters, which we can only use the existing data to feed them. And the good thing is that this hadronization occurs at very long distances compared to the hard scheduling process. And this is by the use of the factorization theorem, we can constrain the model from, for example, lab data, and use the same set of predictions to other processes like dark matter annihilation. Actually, I'm not going to talk a lot about the different excesses, but there are few, for example, from Fermi-Lat, the observed excess over the standard model astrophysical background in gamma ray spectra. There are a lot of studies that have been performed to trying to address and explain this excess. And the most important conclusion is that the precision in the determination of the photon spectra is very important in the fitting procedure, meaning that it depends really, the best fit point depends really on whether you are choosing no uncertainty or uncertainty at all. So therefore, we have to model these QCD uncertainties at least. So before we discuss the uncertainties on photon spectra or particle spectra in general, we have to model this. So basically, we can factorize the whole process into two sets. The first one is kind of dark matter annihilation, that we call it parton level hard process. So it's annihilated to a set of particles which we'll label from X1 to Xn, and this can include intermediate resonances and also finite states, parton level objects like quark and leptons. And then at the end, we can get a lot of hadron level finite states particles like photons and baryons and mesons, etc. So the modeling depends on two things. So basically, it depends on whether this X is electrically charged or contain photons. So we can have, in this case, further QED emissions, which we produce additional photons and charged fermions. On the other hand, there are other complications that if this X has color like top quark or gluon, and therefore we can have a cascade of QCD shower. Then at the end, we have at some low energy scale, which we label here as Q infrared, the shower will stop. And then we start the process of hadronization, which is a process of color naturalization. And this will produce color natural particles like mesons and baryons from color triplets and octet particles. So here I'm giving a sketch of the hadronization process. There are actually two ways to model hadronization. There is either the fragmentation function fit or Monte Carlo hadronization models. And basically hadronization models are what we use in Monte Carlo event generators and basically are based on two different models that exist in the market, such as the cluster hadronization model and the string hadronization model. So this is the hadronization in PYTHIAS 8. So the string model is based on this left-right symmetric function, which gives the probability to produce a hadron at a transverse mass m transverse h and the longitudinal momentum fraction z. And this depends actually on two tunable parameters a and b, and depend also on the hadron transverse mass, which actually we can determine in using data. Okay. And here I'm making like a summary of the different processes that can produce photons in dark matter annihilation. So this is the QED Bremsstrahlung, which dominates at high X, and its relevance for dark matter annihilation into charged leptons and photons. And the corresponding couplings is measured with very high precision. So basically there is no need to discuss the uncertainties on this parameter. Then there is the alpha S, which control the QCD Bremsstrahlung, and this dominates at the bulk and the peak of the photon energy. And basically we can of course assign uncertainty on this parameter. And then there is fragmentation function or hadronization, which basically dominates also in the peak and the bulk of the spectra. And here in this case of photon spectra, we need to tune three parameters, which are flavor independent. So basically photons most of the time in QCD jet, of course. So we are not talking here about photons from dark matter annihilation to leptons or dark matter annihilation to photons, but only in particles that produce QCD object are coming most of the time from the decay of neutral pions. So because the Brescher fraction of pi 0 to gamma gamma is about 100%. So in some cases, if dark matter is annihilating to B quark, and these B quarks are near the threshold, then we can have some photons produced from radiative decays of vector meson B star to B gamma. And then there is the second most important source of photons is from the decay of eta mesons, which occur through two processes, either directly, which eta goes to gamma plus something, or eta goes to pi 0 plus something, and then this pi 0 will go to gamma gamma. Then photons from Bremsstrahlung dominate the extreme of the energy distribution, but the statistics in this region is very small. So for the modeling of gamma rays, there is a tool which is called the particle physics cookbook for dark matter indirect detection, where they provide some recipes for indirect for the indirect detection of dark matter, and mostly they are providing like the flux at the production for different spinel states and different dark matter masses and annihilation channels. And basically they have used PYTHIAS 8.1, which is based on an old tune that has been replaced by the most recent one. And this version of PYTHIAS lacks several capabilities, such as radiation, QCD radiation of heavy particles, electric showers, among others. So it's our aim also to update the flux at the production using the most recent tunings. And so what is the uncertainty on the spectra? First, we perform tunes. As I mentioned, there are three parameters. So there is A and B, and of course we can replace this B by this new parameter with the average of the longitudinal momentum carried by a raw meson. So basically this is kind of a reparameterization of the fragmentation function, which aims to reduce the strong correlation between A and B. And then there is sigma, which is related to the average transverse mass of the hadron. We use a set of lab measurements, and then we include most sensitive observables, and the tuning have been performed using Professor version 2.1.2. And then we added a flat 5% uncertainty on the Monte Carlo predictions in order to reduce the overfit and as extra sanity. So here there is the best fit points. So this without the additional 5% uncertainty, and here with the additional 5% uncertainty. So we can see that the goodness of fit is improved by a factor of 7. And then the uncertainty on the determination of the parameter, or the uncertainty on the best fit points, is also changed. So that's actually is here without 5% uncertainty, you can see that the uncertainty on the parameters is very, very small. This is kind of overfitting issue, which is improved by including this 5% uncertainty. For estimation, the estimates of the hadronization uncertainty, there are 3 methods basically in the market. So the old method is basically, which have been used also by many experimental collaborations, that they use different Monte Carlo event generators, and then they run all these Monte Carlo event generator and define one as a central prediction, and the envelope spanned by all is an estimate of the uncertainty. So this actually it's not very robust, because a lot of Monte Carlo event generator have been tuned to the same existing data, and basically this means that they can have very, very good agreements in most of the regions in a given distribution. And so in some regions you are going to underestimate the uncertainty, and this means that it's not a good point. So a second method, which is provided by Professor, is the eigentunes method, or it's called the Hessian method, in which we diagonalize the covariance matrix around the best fit points, and then we get set of variations, one in the positive and the other one in the negative direction of the eigenvectors. But due to the fact that we have strong correlations, we can have strong correlations. So these eigentunes may give most of the time very small uncertainties. The other one is the manual method, which basically what we do, we choose a set of most sensitive observables, and we remove the outliers. In this study, we choose 15 observables and perform that tune to the parameters of every observable separately. Then we get the 68% confidence level interval of the spread different tunes. This we define as actually as an uncertainty estimate. So here is the result of our method. Basically, here are the different observables, which are the charged moment, which we tune separately, the 3 parameters. And here is the best fit points and the uncertainty on this, which are defined by the green band. And so in order to estimate the uncertainty of the spectra, we should not only get the correlated variation like the plus, 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 or minus, minus, minus for all these 3 parameters, but we have to do all the different uncorrelated variations, like maybe the plus, minus, plus, or whatever, because we have 3 parameters. The number of variations are 26 possible variation, which we include also the nominal prediction. And we find that only cell variations are relevant. And here we study application of this to the case of supersymmetric neutralino with a mass around 85, with a mass around 90 GeV, annihilated to W boson top quark. Here I'm showing the W boson annihilation channel. And so you can see that the blue band and the gray band are shower and the hadronization and the shower uncertainty, and the green line is the Herwig 7 prediction. So we can see that the uncertainty in the peak is not very large. Around the extreme, it can be quite large, between 10 and 15% for the shower and 5 and 30% for the hadronization. So Herwig deviates from PTA in the peak with very large number, but in the extreme by very large number. But in the peak, it's very consistent. Another thing is that the shower uncertainty changed the peak of the distribution, which is not shown here. We have produced the tables for the flux at the production corresponds to gamma rays, positron, and antineutrinos, because positron and antineutrinos have the same physical origin as gamma rays, and we can find the data in Zenodo. So we compare our results to the particle physics cookbook for like we took two example, dark matter mass equal 100 and 1000 GeV, and 2 annihilation channels for the 100 GeV case and 3 annihilation channels for the 1000 GeV case. So we can find that the disagreements in the peak region can be of order of 10 to 20%. The disagreements in the peak is very important as well, especially, for example, for WW. The uncertainty, as you can see, can be of order 10% or more. So we ask people to start using our updates because they provide a lot of improvements. So we studied for the first time the QCD uncertainties relevance for gamma ray dark matter searches within the PYTHIAS event generators, the results of which can be applied also to positrons and antineutrino spectra. We have produced data that you can find it on Zenodo in the form of tables for various final states annihilation, various dark matter masses. And now we are working in progress to provide the uncertainties and the updated spectra, anti-proton spectra relevance, for example, for the AMS experiments. And thank you.